Today, we're going to talk about spontaneous emission and lasers. Lasers are amazing light beams, powerful enough to zoom miles into the sky or cut through lumps of metal. Although they seem pretty recent inventions, they've actually been with us over half a century. The theory was figured out in 1958. The first practical laser was built in 1960. At that time, lasers were thrilling examples of cutting-edge science. Here, Secret Agent 007 James Bond was almost chopped in half by a laser beam in the 1964 film Goldfinger. But apart from Bond villains, no one else had any idea what to do with lasers. Famously, they were described as a solution looking for a problem. Today, we all have lasers in our homes, in CD and DVD players, in our offices, in laser printers, and in the stores where we shop, in barcode scanners. Our clothes are cut with lasers. We fix our eyesight with them. And we send and receive emails over the internet with signals that lasers fire down from fiber optic cables. Whether we realize it or not, all of us use lasers all day long. But how many of us really understand what they are or how they work? In this video, we will learn what spontaneous emission is, the quantum mechanics behind spontaneous emission, and how we use it to make lasers work. Before we talk about spontaneous emission, we need to review what we know about the atom. Just like bricks are the building blocks of a home, atoms are the building blocks of matter. Matter is anything that has mass and takes up space. All matter is made up of atoms. The atom has a nucleus which contains particles of positive charge, the protons, and particles of neutral charge, the neutrons. Surrounding the nucleus of an atom are shells of electrons, which are small negatively charged particles. These shells are actually different energy levels, and within the energy levels, the electrons orbit the nucleus of the atom. The ground state of an electron, here, is the energy level it normally occupies. It is the state of lowest energy for that electron. When an electron temporarily occupies an energy state greater than its ground state, it is in an excited state, like here. An electron can become excited if it is given extra energy, such as if it absorbs a photon or packet of light, or collides with a nearby atom or particle. Each orbital has a specific energy associated with it. For an electron to be boosted to an orbital with a higher energy level, it must overcome the difference in energy between the orbital it is in and the orbital which it is going. This means that it must absorb a photon that contains precisely that amount of energy, or take exactly that amount of energy from another particle in a collision. Electrons do not stay in excited states for very long. They soon return to their ground states, emitting a photon with the same energy as the one that was absorbed. Here. This is what spontaneous emission is. Let's delve into the quantum mechanics of spontaneous emission in a little more detail. Taking the electron transitions associated with visible and ultraviolet interactions with matter as an example, absorption of a photon will occur only when the quantum energy of the photon precisely matches the energy gap between the initial and final states. In the interaction of radiation with matter, if there is no pair of energy states such that the photon energy can elevate the system from the lower to the upper state, then the matter will be transparent to that radiation. Energy levels associated with molecules, atoms, and nuclei are in general discrete quantized energy levels, and transitions between those levels typically involve the absorption or emission of photons. Electron energy levels have been used as an example here, but quantized energy levels for molecular vibration and rotation also exist. Transitions between vibrational quantum states typically occur in the infrared, and transitions between rotational quantum states are typically in the microwave region of the electromagnetic spectrum. It is possible for excited electrons and atoms and molecules to have some other kind of interaction, which lowers their energy before they can make a downward transition. In that case, they would emit a photon of lower energy and longer wavelength. This process is called fluorescence. If it happens essentially instantaneously. It is also possible that material can hold on to the energy of excitation for a long time, gradually making downward transitions with emissions. This delayed emission is called phosphorescence. Since by the Einstein A and B coefficients we know that the probabilities for absorption and emission are the same, the existence of phosphorescence would imply that some interaction took place quickly before the initial absorption that placed the electrons in a much more stable and long-lived state, so that they could not immediately drop back down. In 1917, about 9 years before the development of the relevant quantum theory, Einstein postulated on thermodynamic grounds that the probability for spontaneous emission, A, was related to the probability of simulated emission, B, by that relationship. So this is the relationship we're looking for. And this is what the A-B relationship for Einstein looks like. From the development of the theory behind blackbody radiation, it was known that the equilibrium radiation energy density per unit volume per unit frequency was equal to the exact same thing. Einstein argued that equilibrium would be possible, and the laws of thermodynamics obeyed only if the ratio of the A and B coefficients had the value shown above. This ratio was calculated from quantum mechanics in the mid-1920s. In recognition of Einstein's insight, the coefficients have continued to be called the Einstein A and B coefficients. While applicable in many situations, the A and B coefficients received particular attention in the period in which lasers were being developed. The nature of the coefficients is such that you cannot use the radiation in a cavity to elevate electrons preferentially into an upper state, producing the population inversion necessary for laser action. The particular ratio between the coefficients suggests that the presence of the light to pump electrons into upper states will have the same probability of stimulating an already elevated electron to make the downward transition, so that laser action cannot be achieved with any two-level system. The achievement of laser action was obtained by three-level systems like that in the helium-neon laser, where the population of the upper neon level could be achieved by a non-radiative transfer from the helium gas pumping energy to the neon atoms. That's the quantum explanation of lasers and where it comes from. Now, what we know about spontaneous emission is, how is it used by lasers? What do you need to make a laser? First, we need two basic parts. We need a load of atoms, a solid, liquid, or gas, with electrons in them that we can stimulate. This is known as the medium, or sometimes the amplifying or gain medium, because gain is another word for amplification. Something to stimulate the atoms with, such as a flash tube, like the xenon flash tube you see here, or another laser. A typical red laser would contain a long crystal made of ruby and a flash tube wrapped around it. The flash tube looks a bit like a fluorescent strip light, only it's coiled around the ruby crystal, and it flashes every so often like a camera's flash lamp. And so here is our laser diagram, and we're going to explain the different parts of a laser. So how did the flash tube and the crystal make a laser beam? Well, it starts here in step 1. The high voltage electric supply makes the tube flash on and off. And then 2. Every time the tube flashes, it pumps energy into the ruby crystal. The flashes it makes inject energy into the crystal in the form of photons. So photons are shot into the crystal. 3. Where we're going here. Atoms in the ruby crystal, the large green blobs, soak up this energy in a process called absorption. Atoms absorb energy when their electrons jump to a higher energy level. After a few milliseconds, the electrons return to their original energy level, their ground state, by giving off a photon of light, which are these small blue balls. This is where the spontaneous emission is occurring. At 4, the photons the atoms give off zoom up and down inside the ruby crystal, traveling at the speed of light. Very, very fast. And then 5, every so often, one of these photons stimulates an already excited atom. When this happens, the excited atom gives off a photon, and we get our original photon back as well. This is called stimulated emission. Now, one photon of light is produced too, so the light has been amplified, increased in strength. In other words, light amplification, an increase in the amount of light, has been caused by stimulated emission of radiation. Hence the name laser, because that's exactly how a laser works. 6, we have mirrors. A mirror at one end of the laser tube keeps the photons bouncing back and forth inside the crystal. And then 7, we have a partial mirror at the other end of the tube, bouncing the photons back into the crystal, but lets some escape. Then obviously, the escaping photons form a very concentrated beam of powerful laser light. Hopefully you have enjoyed learning about spontaneous emission and how it makes lasers. If you have any questions, please do not hesitate to contact me at my email, and I will try to help you out, or at least give you a place to start looking for your answer. Thank you.